me to introduce our next speaker, and I'm really happy to have the chance to introduce Professor Claire Gormley. She has recently been appointed full professor of statistics at my school, the School of Mathematics and Statistics at University College in Dublin. I might be a little bit biased as I share with her some research interest. Actually, I had to read her paper during my PhD, let's say. But I really believe that she gave a strong contribution to statistical literature in the last few years. Broadly speaking, in her research, Claire is proposing novel methodologies to deal with high-dimensional data, with complex structure, mixed type ones, and so on and so forth. And she's really into Bayesian and computational statistics with a specific focus on latent variable models, let's say. Last but not least, she's conducting high-level research from an applied point of view, where she's collaborating on different projects in genomics, sports science, political science, etc. And obviously, she has done quite a job on food and nutrition frameworks, both from a, let's say, metabolomic perspective, and recently, also thanks to her involvement with the milk project from a chemometrics one. I have to say that I'm also lucky enough to work with her currently, and it's always a pleasure to have the chance to collaborate with her. And she is the co-director with the CRT, that is this huge Irish center where they are training more than 100 PhD students in the next few years, and she's a PI within the Vista Milk project. Today, Claire is going to talk about statistical methods for predicting cow milk quality traits from routinely available milk spectra, a review of the state of the art and some recent advances. So I leave the floor to Claire. You have 45 minutes in total, including the question, and if you want to answer directly, like live, as Tom did on the chat, or if you want at the end, it's the same for me. Thank you, Claire.
Great. Thanks very much, Alessandro. You can hear me okay?
Yep.
Great, thank you. And I'd like to begin by thanking yourself and Maria Frizarin, Cheryl Nolan and Emer Ferguson for putting together what is really a fantastic 2 days. And I'm aware of all the work that has gone on behind the scenes to do that. So thank you for that. I'll just do the traditional screen sharing thing at this stage. Can you see that okay?
Yep.
If I go, actually, I won't go full screen and then I can see the chat. Okay, can you see it move? Because this happens to me sometimes.
Yes.
Perfect. Okay. So thanks again, Alessandro and Maria, for the invitation to present. I've been taking a slight liberty here, and a bit like Tom, when invited several months ago, I put in a rather broad title, so I've tweaked it very slightly. So what I'll talk about in the first part of the talk today is statistical methods for predicting cow milk quality traits from routinely available milk spectra. And essentially that's sort of a review of the state of the art in that space. And then I think I had said I would talk about recent advances, but I think it's fairer to say I'll talk about scope for advances in this area. As Alessandro said, I'm in the School of Maths and Statistics in University College Dublin, so I'm a statistician, very much learning from the expertise of the animal scientists and food scientists here. But I think it's a really fruitful collaboration, and I think that's a vein you'll see in my talk today, is I think there's huge scope for advancement of both the sort of methodological statistical fields and the application areas. Much of the work today that I'll talk today is not my work, is work of, for example, people like Maria Frizarin, Alessandro, Brendan Murphy, Donna Berry, Sinead McParland, Gifna Mundanda, the list goes on. And at the end, I give links to any of the publications. And as I say, it's with great thanks to them. Okay, so what's the running order for the next 45 minutes or so is to, as I said, first I'll begin by speaking about this work, which is predominantly Maria's, the first paper from Maria's PhD in collaboration with Sinead McParland from Teagasc in Mirror Park. And then I'll take a slight deviation and I'll go back in time and look at some previous work I had done with food scientists where we use probabilistic models for spectral data, and then zoom forward a little in time to think about where is next. Okay, so sort of part one is this work that was it's currently in press, where we look at predicting cow milk quality traits using MIR, using essentially a suite of statistical learning methods. And you'll see very much in this echoes of what Tom spoke about this morning. And I assure you there was no sort of cross communication before I wrote these slides. We just seem to be singing off the same hymn sheet today. So as flagged, this is Maria's work. She is the one who's done the work in the background, and I'll happily defer any of the difficult questions at the end to her. And again, in collaboration with many other co-authors, as you can see here. Okay, so what was the goal of the work? The goal was to evaluate modern statistical machine learning methods and see about their ability to predict both technological traits and protein traits from milk MERS data. As Tom alluded to earlier this morning, you know, PLS, partial least squares, is out there and is working fantastically well. But this was really an exploration and to do that review of the state of the art and see is there anything there that we should be considering. So the technological traits we're considering, and here's where I get out of my depth, are things like Rennie coagulation time, Curd firming time, firmness at 30 and 60 minutes, CMS, as I'll call it for short, pH of the milk samples, and the heat stability. And we'll see sort of different results for these different traits as we move through. And then also for a collection of proteins that are extremely important to be able to infer from the milk sample, for example, for cheese production. Okay, I had this sort of a walkthrough slide of the process, but I think based on the talks this morning, everyone's au fait with this, so I'll jump on. So what were our data? The data were data from Chagask. We had milk samples, so 730 milk samples that were taken from 622 cows. And these were collected over a 1-year period from 7 different research herds. There were morning and evening samples, different parity and different lactation within this data. So lots of variety. Just for sort of info, Maria did remove the water region from our MIR spectra. So here there were 1,060 wavelengths in the original spectra, but here we're only considering about 531. So we do only consider 622 records, and I'll talk to that in a moment. So N is greater than P here, but only slightly. And then we did things like cleaning the data by considering the removal of outliers, and importantly, we removed repeated measures. And I'll speak to this a little later, and Tom touched on it this morning when he talked about experimental design and how important that is in what we're doing. And then a bit like Scott spoke about earlier, here we've used fourfold cross-validation in sort of everything that you see from here on. So how we, for example, removed those repeated measures, what we did there was Maria applied principal components analysis to the data and then removed sort of the least variable of the repeated measures so that we retained as much variation in the data as possible. I'm a statistician, so I can't work with the data unless I see it. So here's a plot of the data just to look at. I think, you know, it's clear there's lots of variety here. Each line here is a spectrum, and there's particular regions, you know, that there's highly variable pieces occurring. Can you see my cursor there, Alessandro? Just to check. Okay, thanks. Okay, so what Maria did was did that sort of review of the state of the art, and what we boiled it down to was exploring 11 regression-based machine learning methods. I can provide these slides afterwards if anyone wishes. I've linked any of the references that are provided. This is a really excellent book called on Statistical Learning, and it gives just a really nice synopsis of all of these methods. So the PDF's available online from the authors, and I'd highly recommend it as a resource. So of the 11, the only ones I'm really going to dwell on today for the sake of time are we considered partial least squares regression, sort of our gold standard, if you wish. The lasso that was mentioned earlier today in the chat, and ridge regression, elastic net, and neural networks. So there were obviously more than that, but they're the sort of the ones that will appear today. Maria also then developed sort of a novel approach, which we call the model averaging approach, where she averaged the predictions that we got from the partial least squares regression, from ridge regression, from lasso, and from the elastic net. So we'll see some results from all of these approaches in the coming slides. For performance assessment in the paper, which again is available if you wish, is we looked at a plethora of different performance assessment measures, but again, for brevity here today, I'm only going to focus on the typical root mean squared error. Okay, so here's, what do the results look like? So here we have, for each of the technological traits, in the first column here, we have what we call the best regression method. And I use the word best sort of in an unsettled way, because what is best? If you use root mean squared error, which is what we used here, this is what was deemed to be the best model. So I suppose the clear thing that is obvious here is that there is no one best model, and it speaks to there's all of these methods are doing roughly the same thing, and you might gain in one data set and lose in another. However, you can see, for example, while we examined 11 different regression methods, they're not all present here. So predominantly it was things like the neural networks, the lasso, that were performing well. Maria's average approach also appeared as a best performer, but then equally good old partially squares regression is still holding its own, for example, when we were predicting pH. And then, not to lose sight of wood for the trees, we need to think of this as not just which is the best, but what are we gaining anything? So here we've compared the percentage change in the root mean squared error and compared to the partially squares results. So you can see, in some places we're gaining very little. So for example, for a 60, we're only gaining by 0.59. But then for heat stability, for example, the neural network is making quite a gain? It's 3%, but it's a marginal improvement on partially squares. And then pretty much similar story when we look at the protein traits. We see, a variety of methods popping up as the best method. So again, no sort of one clear winner. And in some cases, clear draws. For example, in kappa casein, whether you use lasso or average or neural networks, based on the data set we have, you were going to do pretty much as well. And again, focusing then on, okay, well, what is best? How much better than partially squares? Is it worth that piece, as Tom mentioned earlier, of running these massive models and doing lots of tuning and getting results that aren't necessarily reproducible for a gain of, for example, 0.18%. But the gain is still there, and we can't argue with that. Okay, so from sort of that set of results, just to summarize what's there, actually the averaging approach, when you look across all of the traits, was the most frequent best performer in 6 of the 14 traits. Lasso and neural networks perform similarly to the model averaging approach for the kappa casein prediction. Neural networks and ridge regression appear for 3 traits, lasso and PLSR. It's sort of the purpose of these multiple data points is to make clear this point that there wasn't sort of one overall winner. And indeed the gain even for the best models over PLSR was still ranged between 0.18% to 3.67%. So I suppose, I'll get to the take-home message at the end of this, but I think reassuring to see that partially squares regression, which is, what has been widely used, is doing good, and there is an argument to consider some of these other methods. I had this slide in before Georgiana's question this morning, but to talk to the point on interpretability. So for example, while neural networks work very well in several cases, as we all know, they're not hugely interpretable. Whereas, for example, with something like lasso, Maria put together this plot which sort of gives that idea of, for each of the wavelengths here, and you can see each of the traits on the vertical axis, which of the wavelengths were selected by the lasso as being important. And you can see that it varies massively across the different traits. So for example, for RCT, you can see a dot here representing that the wavelength was selected, and the opacity of the dot indicates the number of folds in which it was selected. So for RCT, you can see a lot of the spectrum is really informative. And then for things where lasso actually won, but it was still poorly predicted, was kappa casein. The improvement over PLSR was smaller. It's picking out really, really few wavelengths here, and we can dig in and try and understand what's going on. So I suppose to speak to the fact that the interpretability and being able to understand the output, it's so much more than just looking at that root mean squared error, is sort of part of the message here. And then what we considered was sort of in the same vein. There's partial least squares discriminant analysis, which is widely used for doing classification tasks using spectral data. So sort of in the same vein of, well, in comparison to other methods that are available at present, you know, should we be using something else, or where does PLSR lie within those? So we didn't actually have our classification data or classes. So we did divide our phenotypes here into two classes. So for the milk technological traits, we divide them into two based on the median values. Sort of in line with the thinking that if we can just predict whether it's higher or lower than this median, it quickly tells us something about its suitability for cheese production. For the protein traits, however, they were sort of a lot more variable. So here we divided them into four classes using quartiles. And here again, we considered a number of approaches to classification. So partial least squares discriminant analysis, which is sort of the status quo and does well, but are there better things out there? And then we looked at things like support vector machines, random forests, and boosting decision trees. Again, in the paper, we consider a range of different measures of assessing the performance of the methods. But for what I present here today, I'm only going to sort of talk about accuracy. But again, this point of under the hood, you know, how do we actually decide what a best model is? Very often it varies depending on your measure of performance. I think I see chats coming in, but I don't know if they're for me or someone else. No. Okay, so for the classification approaches then to our technological traits, here again I have the different traits listed, and then the best method based on the accuracy across the fourfold cross validation. And it's a very clear story in the technological traits. PLSDA is there and is holding its own, but it's definitely accompanied by support vector machines. An important piece, however, is not to lose sight of the wood for the trees. So, you know, these are the best methods, but how accurate are they actually being? And for the technological traits, they're not doing too badly. Like for pH, we're getting an accuracy of 0.8, but then it is as low as, let's say, 0.62 for CMS. For the protein traits, however, it's quite a different story. Well, so we still are seeing partially squares discriminant analysis popping up as sort of the best method, but random forest is also appearing now. But again, not to lose sight of the wood for the trees here, the accuracies of the resulting classifications, and they're really not, they're all around the 0.4 mark there. And I think I think that Maria's work has shown exactly what Tom mentioned earlier is, you know, if you have these continuous valued variables, you're better off working with those. But what this piece shows is, you know, should you have class type data or binary traits, you know, there are another range of methods in additional to partially squares discriminant analysis that you might consider using because their performance is competitive. So again, just to sort of summarize the piece where we were looking at classification methods, the support vector machine definitely performed very well there, but PLSDA was hot on its heels. Our accuracy was quite strong for the technological traits, from about 0.8 to 0.62. And then in terms of the protein traits, partially squares did well there. Support vector machine and random forest appeared, but our accuracy was low. But overall, what's sort of, so, you know, Maria did a huge amount of work applying all of these methods to a wide range of traits. So what do we do when we zoom out of that and say, okay, well, what's the overall message? Again, as Tom said this morning, you know, simpler methods are preferred to more complicated methods if your results are comparable. So if your root mean squared error is marginally different between the two, going for the more interpretable approach, like partially squares, where you can look at the coefficients, or like the Lasso, where you can look at the coefficients, are going to be more interpretable, more reproducible, which I'm interested to hear about this afternoon, and involves fewer tuning parameters. The best method varies, so there is no one sort of message that we're saying, oh, this is the one you should use. It's going to vary depending on, you know, what's in the data that you're actually looking at. but are at the same time, what Maria's work has shown is that there are other methods there that are very competitive, and if you're just really focused on that the prediction piece, there are other novel statistical machine learning methods that may improve the prediction of milk traits, and in particular I'd call out Maria's averaging method that performs very well. However, we shouldn't throw the baby out with the bathwater. The partial least squares based methods are still performing very competitively. Again, with a link to this afternoon's talk on reproducibility, Maria put all of her code that she used to produce the paper on her GitHub page, so everything is there if anyone else wants to see how she did it, or to apply any of the methods that we considered to their data. And as I say, we explored more methods than I have just spoken about here today, but in the interest of time, I only presented those that sort of appeared in the set of being best models. Let's see. Question. Okay, so so that's very much the sort of the main piece of the title, which was using or exploring other statistical machine learning methods to see can we improve prediction for milk traits. And then the second piece I wanted to talk about is some work I had done. It's now many years ago. I was shocked last night when I looked at the date on some of these papers, but it's really where I started working with spectral data, but it was within a metabolomics or more of a food science application area. And this is where we use probabilistic models to analyze spectral data, sort of in slight contrast, but not completely to the methods that Maria's work looked at. And really what I want to do here is sort of go through some of those approaches. As I say, some of them are now quite old, and then, but with a view to talking to where I see potential gains in advancing both sort of fields. Okay, so principal components analysis, or PCA, is I'm sure known to every person on the call here. It's a really well known and well utilized dimension reduction tool. Reduces the dimension of the spectral data and accounts for as much of the variation as possible. And it's used ubiquitously. For example, Maria used it in order to choose which of the repeated measures that we retained in our data set. It's used to visualize our data. It's used as part of principal components regression. So it's really widely used in the context of spectral data. However, it has challenges. We have to choose a number of dimensions. It has it's just an eigenvector decomposition of a covariance matrix, so it's difficult to sort of incorporate any sort of additional information that you have. So for example, Tom called out experimental design. So the fact that we had repeated measures, you can't put that into principal components analysis. It doesn't sort of have the flexibility to be extended in any way. So actually recently, a PhD student of Tom's did a really nice PhD thesis, which is available on the UCL website, where they did look at a principal components analysis and took account of class labels, so classification, when constructing principal components analysis with the view to improving the classification accuracy. And it was applied to NIR data. I'm sure Tom can speak more on that if needed. But it was a really nice example of trying to think of principal components analysis as more than just being an eigenvector decomposition, and can we actually sort of embed it in the problem that we're trying to solve. So then again, way back nearly 20 years ago now, there was a really seminal paper in the statistics field by Tipping and Christopher Bishop, where they established, or they showed that principal components analysis, the traditional one that we all use, is exactly equivalent to what's called probabilistic principal components analysis, which is founded on a statistical model. So why is this, if we have two things that are exactly the same, why would we use the probabilistic approach to just plain old PCA? And it's exactly for this reason that the statistical modeling framework that underpins PPCA, as I'll call it, it gives us freedom to do model extensions. So so for example, it allows us to include covariate data. So you might have weights of animals or parity and all of those things that are available, and we can't currently incorporate in methods like principal components analysis. We could model the fact that we have dependent observations, so account for the fact that we have repeated measures rather than either throwing away data or including data that we know are going to give us biased estimates of our parameters. We can extend it then to doing things like clustering, which I'll touch on. And importantly, to sort of jump back to this the higher bullet point, is it allows us ways to do principled model selection. So once we have a statistical model, we can use statistical theoretically underpinned model selection criteria to, for example, choose the number of principal components that we should retain. So rather than eyeballing a scree plot and trying to decide what the right value is, here we sort of have an objective, statistically motivated way. Okay, so this is kind of one slide. So I have to do one slide of equations. So this is it. So probabilistic PCA is just a probabilistic latent variable model. So if most people would be used to in principal components analysis, you visualize the principal component scores in this lower dimensional space. So here I'm going to represent each of those scores, say of the ith animal in this reduced dimensional space, by a latent variable, which I'll call Z. So this is the location or the principal component score of observation I in a Q dimensional principal subspace. Typically we look at pictures where Q is 2, but Q must or may be much, much higher than that, particularly in spectral data where P is high. So Tipping and Bishop showed that if you assume that these principal component scores follow a multivariate normal distribution that has Q dimensions, mean 0 and identity covariance matrix, that the actual model it turns out to be equivalent to PCA. So if Xi then is just a spectrum from animal I, it's a vector of length P in the statistical setting. So if you model that spectrum as simply a linear function of those latent principal component scores, where W here is the loadings matrix that we'd be used to sort of hearing in the principal components language, plus some mean and some variance, where this variance is also assumed to be multivariate normal with a diagonal covariance matrix. And I'll talk a little later about this important diagonal covariance matrix. So just to flag that the sigma squared here piece is important later. So essentially all this is saying actually we can, if we model our spectrum as a linear function of these latent scores, it turns out they are the same as the principal component scores. And because we have a distribution, then we can use all of the properties of the statistical distribution. So we can write down things like, well, what's the distribution of the spectrum given the principal component score, or what's the marginal, what's the distribution of just the data. And once we have a model, then we can, sorry, I'm jumping. Once we have a model, then we can estimate parameters, we can talk about uncertainty in our parameters, and it turns out it's all completely equivalent asymptotically to probabilistic PCA. I've stolen here what I think is a really great plot from Christopher Bishop's, again, really excellent book, Pattern Recognition and Machine Learning, that I think shows sort of the slightly different view of probabilistic principal components analysis, and this generative view of statistical modeling that I think is really the place where there is big scope for further development in chemometrics broadly. So typically we think of principal components analysis as being a projection of our high dimensional data into a low dimensional space, whereas probabilistic principal components analysis thinks of it in exactly the other way. It's a generative model. We assume there is some true underlying value principal component score, which is Z. It has a Gaussian, standard Gaussian distribution. We generate a value of Z, we multiply it by our loadings matrix and add on our mean, and that gives us our final spectrum. So it's viewing this entire process sort of from the ground up rather than the sky down. And then what we get are things like, now you can see the red ellipses here represent the contours of a Gaussian distribution, or in this final panel where we're actually just viewing the marginal distribution of your spectrum. So it's a slightly different way of thinking about all of this, but it has a statistical model underneath it. So we can get things like maximum likelihood estimates of the loadings, the mean and this variance, you can get them analytically or using an iterative algorithm, or you have a statistical model, so you can use a Bayesian framework, put some priors on our parameters and use a Bayesian framework to do inference. Once you have a statistical model, it's sort of the world of what's possible can open up. And then I suppose the key message of the paper was that they showed that the columns of W, the columns of this maximum likelihood estimate of your loadings matrix exactly span the principal subspace. So asymptotically, probabilistic PCA and plain old PCA are exactly the same. What we can then do, because we have distributions, we can then, for example, write down things like the posterior distribution of our principal component score. So we don't just get an estimate of the principal component score, but we get a distribution around that, and that can be very, as usual, it's really important to consider the uncertainty in these. Okay, so some examples. That's the kind of the statsy bit over. Sorry, I see some questions, but not me. Okay, so this is work was thanks to Professor Lorraine Brennan in the Conway Institute in UCD. So she's a metabolomic scientist, and this was data that was generated in her lab a long time ago, and was work done by our joint PhD student Gifna Mandanda. So Lorraine had this time NMR spectral data from urine samples from a treatment and control group with the same number of observations in each. We had 18 spectral profiles, so 18 observations, tiny, and about 190 spectral bins in our spectrum. But additionally, there was a covariate associated with each of the observations, which was the weight of each of those subjects. So again, what did the data look like? Here are our 18 spectra, 9 disease and 9 control. And you can see, as usual, there's variation here and different things happening in the metabolomic spectrum, depending on your disease status. So what we did was applied probabilistic principal components analysis to these. We wanted to reduce the dimension of these spectra and have a look at them. We wanted to do a few other things, and I'll talk about that in a moment. But first, we just wanted to do, visualize these. So we looked at probabilistic PCA. The benefit of probabilistic PCA is we can use these model selection tools to select the optimal number of components. So we're most often used to seeing principal components analysis, and you'll be used to seeing this like lower red line here, where we eyeball the proportion of the variation explained, and we try to decide, well, should I choose 3 or should I choose 6, or what is the number of principal components. Here in black line is what's called the BIC value, or the Bayesian information criterion value, which is based on the fit of the statistical model, the probabilistic PCA here, but where we penalize for having overly complex models. And here we get a very clear message, higher is better, that actually 5 principal components is the number of principal components that best fits this particular data set. So it brings that advantage of objectivity to your selection. And then equally, here's a typical plot you'll be used to seeing, a 2-dimensional principal component scores plot. A dot is a control subject, a triangle is a treatment subject. But their location is actually the posterior mean of the principal component score. But here we also get the little ellipses show an indication of the uncertainty associated with that's available, because we actually get the posterior distribution here rather than just a point value. So that's nothing new. We were just taking Tipping and Bishop's work and applying it, but Lorraine had this extra covariate that she would have liked to have been included. And this led to the development of what we call PPCCA, where we included probabilistic principal components and covariates analysis. So because we have a statistical model underneath, we can extend it, and we did that to jointly model the covariates and the spectral data. So what's the simple motivation? Maybe the covariates associated with an observation influence their location in that principal subspace, and can we at least explore if it is having an impact? So we have a model. So this is one way in which we did that. We said, okay, instead of assuming our latent scores, our principal component scores are multivariate normal with mean 0, here we assumed that the mean was equal to delta, where this delta was simply a linear regression on any covariates that were available. So we model the mean delta as this linear regression of weight. In this case, it actually doesn't change our inference on the number of principal components that are required. And if we just look at the first 2 of them, the overall locations haven't changed hugely. So the dots here, again, are the control and treatment subjects, and the size of the dot relates to the weight of the subject. But now we have parameter estimates associated with our regression model, so we can actually see, well, is weight, impacting on the principal components scores. So when we dug into those, it actually showed it did have actually a negative coefficient on principal component 2, but wasn't contributing at all to principal component 1, which is very clearly where the variation between treatment and control groups is being drawn out, giving insight to the sort of the non-effect of weight here. Okay, and then to sort of another extension, which it tracks back to Maria's work, where we had these repeated measures, and because of lots of the assumptions that underpin those statistical machine learning methods that Maria looked at, that if you dig deep enough, assume that all of your observations are independent, we had to remove the repeated measures. So this is an example where because we had a probabilistic model, we could actually build in the fact that we have repeated measures and directly model that. So this was where we developed what we call dynamic probabilistic PCA, or it's how we can extend PPCA to look at longitudinal data. So here we had 15 subjects. It was again the same study of Lorraine's, 8 treated, 7 control, the same number of bins, and 8 different time points. And what we did here was just, built that into the model. So we can say, actually, we want to do dimension reduction here, but I want to take account of the fact that I have 8 repeated measures. And also I'd be interested in sort of seeing how those observations move in the reduced dimensional space across time in this case. And I'd also be interested to see, well, which of the spectral bins or underlying metabolites change across time. So here we developed what we call dynamic, or DPPCA, with the very slight change. So here again, we still have that our spectrum for observation I at time point M is still just a linear function of our principal component score from observation I at time point M, where we have a loadings matrix separate for each time point, and we have an error. And how we built that dependency in is we simply model the variances of the latent scores, and that sigma squared I covariance matrix that I called out earlier, the variance of the errors. We allowed them to follow a stationary first order autoregressive process, so that the dependency was modeled as we moved across time. And here, again, it's just a statistical model, so GIF did the inference using a Bayesian framework. Okay, so what does this allow us to do? It allows us to visualize the data in a reduced dimensional space. And we get, for example, things like what we call the trajectory. So here I've sampled just 2 different subjects, 1 control subject, 1 treatment subject, and each of the numbers indicate the 8 time points. So what we've done here is we get an estimate of their location in their principal component space that's specific to each time point, but here we've mapped them all into the first time point. But all of this has directly modeled the dependency that is present in the data. So you can see, we looked at this for several subjects, but it's very clear that the variation and the movement within the principal component space is much more variable in the treatment group than in the control group. And in other words, the metabolism and the metabolites are varying or much more volatile in the treatment group. And then really, like, Lorraine's key question for us was, well, what's changing over time? Which are the metabolites that are changing over time? We have tiny n here, 15 and 190 bins in our spectrum. So how do you go about pulling out which of those vary over time? So we used the probabilistic principal components to highlight the sort of highest loading spectral bins, so the most important spectral bins. And then we were able to fit just simple linear mixed models here. And here's an example of the profile of 2 spectral bins, 2.46 and 3.02, in the left in the treatment group and in the right on the control group. And you can see that the evolution or the behavior of these the spectra at these points, which relates to metabolite, which is 2-oxoglutarate, is completely different between the 2. But these have been pulled out sort of from the data while accounting for the fact that, well, here n is much less than p, and for the dependency in the data. Okay, and then final piece on banging this drum about probabilistic models is once we have a model, we can then do things like clustering and classification in a probabilistic way, and this is a particular area of research focus in our group in UCD. So back in 2005, Nima Dean, Brendan Murphy, who's on the call, and Jared Downey, who's also from Chagask, they had a really nice paper where they developed a classification method where they had both labeled and unlabeled BIS and NIR data in food authenticity studies. And what's under the hood there is an approach that relies on what's called a mixture model, or essentially where we combine lots of these multivariate normal Gaussian distributions together. So sort of in the same vein, saying, well, if we have a statistical model, then we can actually use that to do, in this case, semi-supervised classification. Equally, Tipping and Bishop had developed a mixture of these probabilistic PCA models that allowed us to sort of jointly do do clustering and dimension reduction. So clustering, where we don't know the classes and we're seeking out subgroups. And then last year, with a PhD student, Keith Murphy, he developed a Bayesian non-parametric approach to this, essentially Tipping and Bishop's mixture of PPCA models that allows sort of automatic inference of the number of principal components that are in the model and specifically within each cluster. So it uses a Bayesian non-parametric prior that essentially allows an infinite number of principal components underlying the data and shrinks the loadings associated with those as you move into higher numbers of principal components. So what this gives us then is, if you're trying to say cluster Lorraine's data, the NMR data, what we get is not just a clustering which says, okay, well, these are the observations that belong to, in our case, 2 groups was suggested. That's another research topic, but allows you to within each of the groups allow the flexibility that you might have different numbers of principal components underlying your data within each cluster. So here the posterior distribution of Q sub G, so this is the number of principal components specific to cluster G, is allowed to vary. And because we do it in a Bayesian framework, we get a full distribution around that. So what we're showing here is the number of increasing principal components, if you want to think of it on the horizontal axis, and the frequency being the number of samples from our MCMC chain at which this number of principal components was populated. And what we see is in cluster 1 is the posterior distribution for the purple cluster, and in green is the posterior distribution for cluster 2. And it turns out that second cluster contained all of the treatment subjects, and it's clear here that, you know, if you look at the modal value, the modal number of principal components in the treatment group is 5, so it needs 5 principal components to capture that information in the data, whereas for the healthy group, with the non-disease group, we only need 3. So there's much more complexity in the spectra underpinning the treatment group. And by having the modeling flexibility and objectivity built in, we're not having to make sort of subjective decisions around this. So as I say, it was going back in time a good bit, but I suppose had done lots of these work in these probabilistic models for spectral data, and then more recently the work with Maria and Sinead on these more statistical learning methods, and it really made me think about, well, where to next? Where, you know, there's huge scope for advances here, you know, the merging of you know, the state of the art in chemometrics with all of these probabilistic approaches, I think is a huge area that has huge potential. You know, I remember having this conversation with Alessandro maybe a year ago. You know, if there was a probabilistic version of partial least squares, you know, we'd be home and dry. And if there is, someone let me know, please, because then we could, you know, build in covariates, build in dependency across time, and still have all those wonderful properties of partial least squares that Maria's work has demonstrated are still competitive with the current methods. There has been some work done on this, and again, many of these references are quite old. So if other people are aware of other work in this area, I'd be really open to hearing about it. So there was a paper back in 2007 where they did consider covariate adjustment in partial least squares, and also another paper in 2010 where they developed sort of essentially partial least squares discriminant analysis that directly counts for that experimental design, and that Tom spoke to, that accounts for the fact that in the case of the NMR data they were looking at, the data came from a crossover design and you had dependency among that set of observations. I suppose that, you know, I think embedding approaches in these statistical modeling frameworks allows us reproducibility, which is crucial at the best of times, but it's becoming more and more important in the type of work we do, and allows the removal of those subjective choices and so much tuning and all those parameters that are very much hidden under the hood, when we see that, you know, high line result of how a method performs. So what's the take-home message, I suppose? I think Maria's work showed that there's really good methods out there. So yeah, you know, we should go explore and use them. But we really need to be cognizant of the assumptions that underpin them. If you dig deep enough, from what I've seen, like so many of them assume, for example, that the rows or the observations in your data set are independent. The methods will still run, but they will give us biased estimates, and we know that. But I think the nice piece is kind of, and where I see the scope for advancements in both sort of the statistical methodology world and in the application of these methods in the context of chemometrics, is that there's much more work to do, and I think huge potential to advance sort of both fields alongside each other. And I'll conclude with that. I'll leave, as I say, these links are live, so I can circulate the slides if anyone is interested in them. That's the link to Maria's paper. This was the work of Gift Nayamandanda many years ago, where we developed the probabilistic PCA with the covariates piece, and he had an associated R package to do with that. The dynamic PPCA was published in Journal of the Royal Statistical Society, Series C, and it doesn't have an R package, but the code is available with the paper. And then Keith Murphy's work last year in what's called an infinite mixture of infinite factor analyzers, which gave that posterior distribution for the number of factors, and his really excellent associated R package called IMIFA. They're all there and available. Thanks very much.
Thank you, Claire. We are running a bit late, but there are some questions in the chat you might want to answer to. It was actually Tom asking if did you try any probabilistic classification methods and start described in the Maria's work, let's say.
No, good point. Actually, no, we not for any particular reason. Just didn't think of it. But yeah, that's a very good idea.
But I can jump in because I'm working on it actually.
Great.
Yeah, I can answer Tom because I'm working on it on a different set of data, like in classification we are using with Brendan, and also Maria is involved as a side project of her PhD, but we are working on it. And they perform quite well, in my opinion, and they are more interpretable because of all the things that Claire said. Actually, you can try to embed a lot of stuff inside your model and try to interpret a bit better. I'm a huge fan, actually, and the results are comparable, I would say. And then there's a question about Donna. It's quite long. It's the usual Donna type question, starting with completely ignorant question, but at the end it's not ignorant at all.
So your last piece there, Donna, about violating a few model assumptions, like this is just sort of the fact of that we all do in modeling. We know the model's wrong. It's useful. It's going to be more useful if we adhere to the model assumptions. Very often the code will still run and the model will give you some sort of output, but we just know it will be better output. There will be less bias and less variation in our resulting, for example, parameter estimates if we do adhere to the assumptions that underpin the model. So, you know, in a sense, there's no reason that you couldn't just stick the covariate in, you know, press go, R will compute and give you an answer. But it's whether that answer, whether the model makes sense, and whether, you know, the impact that could be having on the bias of your parameter estimates. And then, oh, I'm intrigued. What's, sorry, Laura, what's CPPLS? Yes, so this is my my hunch, and I just haven't done enough work on it. I have there's a postdoctoral researcher in Insight, Susie Horisky, I think is on the call, is beginning to look at these types of more probabilistic approaches to these regression methods for spectral data, and this is where, you know, there are connotations or clear sort of synergies with canonical correlation analysis. So I had wondered, was there anything done in that area to date? I couldn't have been the first person to sort of see that. So thanks, I'll definitely look up canonical powered partial least squares.
And there was also a quick question by Maria. If there are other methods as simple as PCA for data visualization, let's say.
So things like multidimensional scaling, I suppose, is a what turns out can be equivalent to PCA depending on how you've scaled your data. Then there's, so actually I lied a little bit. So Keith's work actually developed what was called a factor analysis model. PCA is a constrained version of factor analysis. So there are sort of other methods that are there. Yep, definitely, but possibly not as simple as PCA.
Yeah, I have a question, a comment, something that we commented on together. Like, Maria removed some region of the spectra when doing that kind of analysis. She ended up working with 500 and something wavelengths there instead of whole spectrum. Well, it's linked somehow to what Tom said before. It's like a take-home message I would like to take on myself, because Tom was referring to Karl Norris, like looking at the wavelength and say, okay, this is relevant, this is not relevant, at the beginning of the chemometrics stuff here. And it's something that somehow we are missing now, probably also because of the amount of different applications we might have with this kind of data. And it's difficult because we in that specific case, we have some indication that those regions that we are removing are water related or something, noisy, let's say, but we're not completely sure. It's like, take-home message is probably that we need, I don't know if you agree, but we need a bit more like communication with people really knowing what is going on there, like as Karl Norris was doing at the beginning of the stuff here. It was more than a comment, more than a question.
No, I completely agree. And in a sense, this is why, for example, VistaMilk is so great, because you don't have statisticians blindly working with numbers, nor the applied scientists applying methods that mightn't actually be suitable. So completely agree. The collaboration and communication piece has such a big impact on what actually results.
Okay, if there are no other questions, we are running a bit late. So I think we can conclude here the morning part of day one of our workshop. And we should have our lunch break, and we are going to come back at 2 p.m. Sorry, I'm in Italian time zone, so I try to convert everything. Yeah, we're going to come back to 2 p.m. Irish time. Thank you very much.